a telescope has revealed something that quietly overturns our sense of scale. For a long time, the universe was described in simple terms. It is about 13.5 billion years old. Light has had that long to travel. So the visible universe should extend roughly 13.5 billion light-years in every direction. That conclusion feels reasonable. It is also wrong. The observable universe spans about 93 billion light-years from one side to the other. Not because the universe is older than we thought, but because space itself has been expanding while light has been in transit. James Webb did not change the age of the cosmos. It revealed the consequences of expansion with unprecedented clarity. When Webb focused on regions of sky that appeared nearly empty, it did not find darkness. It found depth, layers of galaxies stacked behind one another, extending back toward the earliest measurable moments after the Big Bang. Some of the light Webb detects began its journey when the universe was only a few 100 million years old. At that time, Earth did not exist. Our sun had not formed. The Milky Way was still assembling from diffuse gas and dark matter. What Webb observes is not distance alone. It is time. Every image represents a moment preserved in light, carried across an expanding universe for almost its entire history. Those photons passed through eras when stars were born and died, when galaxies merged, and when cosmic structure took shape. And what they reveal challenges long-standing expectations. Galaxies appear earlier than predicted, brighter than expected, and more massive than theory allows. Black holes exist when there should not have been enough time for them to grow. Large-scale structures are already emerging when the universe was still in its infancy. The early universe was expected to be sparse and simple. Instead, it appears active, luminous, and unexpectedly complex. James Webb is not merely extending our view. It is forcing us to reconsider how quickly the universe learned to build itself. To understand why Webb can see so far, it helps to start with a simple fact. Light does not arrive instantly. When light leaves an object, it travels at a fixed speed. Even across everyday distances, that speed introduces a delay. Across cosmic distances, the delay becomes the story itself. When we observe a distant galaxy, we are not seeing it as it is now. We are seeing it as it was when the light began its journey. Every increase in distance pushes that image further into the past. This means astronomy is also archaeology. James Webb was designed specifically to read these ancient signals. Its primary mirror spans just over 21 feet and is coated in gold to reflect infrared wavelengths efficiently. Infrared light is crucial because the universe expands. As space stretches, the wavelength of traveling light stretches with it. Ultraviolet light becomes visible light. Visible light becomes infrared. Light that began its journey blue and energetic arrives long, faint, and red. This effect is called redshift, and it is one of the most important tools in cosmology. The farther a galaxy is, the more its light has been stretched. By measuring how far known spectral lines have shifted, scientists can calculate how much the universe has expanded since that light was emitted. This provides both distance and age. Webb operates far from Earth, near the second Lagrange point, where it remains cold and shielded from our planet's heat and glare. This allows it to detect extremely faint infrared signals that would be drowned out closer to Earth. In one of its deepest observations, Webb gathered light for many hours to capture galaxies so distant that their photons have been traveling for more than 13 billion years. Those photons began their journey when the universe was only a few 100 million years old. At that time, the cosmos was undergoing a transition known as cosmic dawn. The first generations of stars were ignited. The first galaxies were beginning to assemble. Hydrogen gas was being transformed into light for the first time since the universe became transparent. According to long-standing models, this era should have been quiet and sparse. Small protogalaxies, few stars, slow growth. Webb sees something very different. Among the most surprising discoveries are galaxies that appear far too bright for their age. Some are compact, but others are already extended structures, containing hundreds of millions of times the mass of our Sun in stars. Their spectra show light produced by young stellar populations, not by older, dimmer stars. These galaxies are actively forming stars at rates that should not be possible so early in cosmic history. Even more puzzling, some of these galaxies contain heavy elements such as carbon and oxygen. These elements do not form in the Big Bang. They are forged inside stars and dispersed when those stars die. For such elements to exist, an earlier generation of stars must already have lived and died. That pushes the timeline of star formation even further back. Astronomers confirmed the distances of these objects using Webb spectrographs, instruments that split incoming light into its component wavelengths. One confirmed galaxy shows a redshift greater than 14, meaning the universe has expanded more than 15 times since its light was emitted. When that light began its journey, space was far denser, far hotter, and far smaller than it is today. The existence of such galaxies creates a fundamental problem. Structure formation is governed by gravity, and gravity works gradually. Gas must cool before it can collapse. Stars take millions of years to form. Dark matter halos must grow large enough to pull ordinary matter inward. Current models account for all of this and predict how quickly galaxies should appear and grow. Webb's observations exceed those predictions. Not by a small margin. In multiple surveys, Webb has found several times more galaxies in the early universe than theory allows. These are not isolated anomalies. They appear again and again in different regions of the sky, observed with different instruments. The early universe appears to have been far more efficient at building stars and galaxies than our models predict. This raises difficult questions. Did stars form differently in the early universe? Did gas collapse more rapidly under denser conditions? Did dark matter behave in ways we do not yet understand? Or is something missing from our description of how structure emerged? These questions matter because they affect everything that follows. If galaxies formed earlier and faster, then they began influencing their surroundings sooner. They would have started ionizing the surrounding hydrogen earlier. They would have enriched space with heavy elements more quickly. They would have accelerated the formation of larger cosmic structures. In other words, the entire timeline of cosmic evolution may need adjustment. And this brings us back to the scale of the universe itself. Light has been traveling toward us for about 13 8/10 billion years since the Big Bang. Yet the most distant objects we can observe are now more than 46 billion light-years away. This seems impossible at first glance. Nothing can move faster than light. So how can anything be farther away than light could have traveled? The answer is expansion. Galaxies are not racing through space away from us. Space itself is stretching between us and them. When a distant galaxy emitted the light we now detect, it was much closer than it is today. As the light traveled, the space it crossed expanded. By the time that light reached us, the source had been carried far beyond its original distance. This is why the observable universe forms a sphere with a radius of about 46.5 billion light-years, even though the universe is only 13 8/10 billion years old. The observable universe is not the entire universe. It is only the region from which light has had time to reach us. Beyond that boundary, space continues. Galaxies exist there. Stars form and die. Planets orbit unseen suns. But no signal from those regions can ever reach Earth. This is the cosmic horizon. As expansion accelerates, that horizon changes. More galaxies slip beyond it. Their light becomes increasingly redshifted, stretched until it fades beyond detectability. Over immense spans of time, even galaxies we can see today will disappear from view. What Webb has done is capture this universe at a rare moment. A moment when light from the earliest galaxies is still arriving. When the record of cosmic history has not yet been erased by expansion. It has shown us that the universe was already busy, already structured, and already luminous far earlier than expected. And it has made something else clear. The universe is not only larger than we imagined. It is more active, more crowded, and more complex, even at its beginning. This expansion is not slowing down. In the late 20th century, astronomers expected gravity to be gradually reducing the rate at which the universe expands. Matter attracts matter. Over billions of years, that attraction should act as a brake. Observations showed the opposite. By studying distant type ER supernova, astronomers discovered that expansion is accelerating. These supernova explode with remarkably consistent brightness, which allows scientists to compare how bright they appear with how bright they should be. The difference reveals distance. When those distances were compared with redshift measurements, the result was unexpected. The most distant supernova were farther away than predicted. The universe had been expanding more slowly in the past and faster in the present. Something was pushing space apart. That influence is called dark energy. Dark energy is not a substance in the usual sense. It does not clump. It does not form structures. It appears to be a property of space itself. Its most unusual feature is how it behaves as the universe expands. Normal matter becomes diluted as space grows. Radiation becomes weaker as wavelengths stretch. Dark energy does neither. As space expands, the density of dark energy remains essentially constant. When there is more space, there is more dark energy. This creates a tipping point in cosmic history. Early in the universe, matter dominated. Gravity shaped galaxies, clusters, and filaments. But as expansion continued, matter spread out and weakened. Dark energy did not. About 5 billion years ago, dark energy overtook matter as the dominant influence on cosmic evolution. From that moment onward, expansion began accelerating. This acceleration explains why the observable universe spans 93 billion light-years, even though light has only been traveling for 13 8/10 billion years. Dark energy also determines the universe's long-term future. If its strength remains constant, expansion will continue accelerating indefinitely. Gravitationally bound systems like galaxy clusters will remain intact. But everything beyond our local group will eventually pass beyond the cosmic horizon. Trillions of years from now, observers in our galaxy would see only nearby companions. The rest of the universe would be unreachable, its light stretched beyond detection. If dark energy grows stronger with time, the outcome could be more extreme. In a scenario known as the Big Rip, expansion would eventually overcome gravity on smaller and smaller scales. Clusters would dissolve. Galaxies would tear apart. Star systems would separate. Even atoms could be pulled apart by the expansion of space. Current measurements suggest dark energy behaves like a cosmological constant, with an equation of state close to -1. This corresponds to a constant energy density built into space itself, similar to what Einstein once proposed. But measuring dark energy precisely is difficult. small uncertainties leave room for different possibilities. Astronomers continue to observe supernova, map galaxy distributions, and measure large-scale structure to refine these values. What is certain is that dark energy exists, dominates the universe today, and controls its fate. As space expands, it also affects time. According to relativity, motion and gravity influence the rate at which time passes. Objects moving at high relative speeds experience time differently from slower moving ones. At the largest scales, cosmic expansion creates extreme relative velocities. Galaxies near the edge of the observable universe appear to be receding at speeds approaching the speed of light. From our perspective, time in those distant galaxies appears slowed. Their evolution seems frozen at a particular moment. From their perspective, the same is true of us. Time dilation is not absolute. It depends on the observer. As expansion accelerates, galaxies cross the cosmic horizon. Once beyond it, no signal they emit will ever reach us. From our viewpoint, their clocks appear to slow and then stop at the horizon. Closer galaxies experience less extreme effects. Members of the local group are gravitationally bound and not participating in expansion at all. This creates a universe layered in time. The farthest galaxies we observe appear as they were near the beginning. Intermediate galaxies show later stages. Nearby galaxies reflect the present. James Webb observes this entire gradient at once. It sees ancient galaxies frozen near cosmic dawn, others partway through evolution, and nearby systems in mature states. All of this appears in a single field of view, compressed into light. This ability to see across time depends on wavelength. Earlier telescopes such as Hubble operated primarily in visible and ultraviolet light. That works well for nearby galaxies whose light has not been heavily stretched. But for the most distant galaxies, visible light has been shifted entirely into infrared. Hubble could not see them. James Webb was designed for this purpose. Its instruments cover wavelengths from near-infrared to mid-infrared, allowing it to detect light stretched by factors greater than 10. To do this, the telescope operates at extremely low temperatures, preventing its own heat from overwhelming faint signals. When Webb revisited regions Hubble had studied for decades, the difference was immediate. Areas that appeared nearly empty in visible light filled with galaxies in infrared. Faint red smudges became clear structures. Dusty regions once opaque revealed star-forming activity within. The darkness had never been empty. It had been invisible. Webb's images show that the universe contains far more galaxies than previously estimated. Deep field surveys reveal hundreds of thousands of galaxies in regions once thought to contain only thousands. If these densities are representative, the total number of galaxies in the observable universe could be far higher than earlier estimates. This changes how we think about scale. Each galaxy contains billions or trillions of stars. Each star may host planets. As galaxy counts rise, so does every estimate of cosmic population. Yet even this vast observable realm represents only a fraction of what exists. The universe extends beyond our horizon. Whether it is finite or infinite remains unknown. What we can say with confidence is that we see only what light has had time to show us. James Webb has expanded that view deeper than ever before. And what it reveals is a universe that formed structure quickly, evolved rapidly, and reached complexity far earlier than expected. When astronomers compare Webb's observations with earlier surveys, the difference is not subtle. The Hubble Space Telescope transformed astronomy for more than 3 decades. Its deep field images revealed thousands of galaxies in tiny patches of sky, changing our understanding of the universe's scale. For a long time, Those images represented the deepest views ever obtained. But Hubble was limited by wavelength. It observed primarily invisible and ultraviolet light with modest near-infrared capability. That meant it could see nearby and intermediate distance galaxies clearly, but it struggled with the most distant ones. Light from the earliest galaxies had been stretched beyond Hubble's sensitivity. When Webb examined the same regions, it saw far more. Places where Hubble detected a few thousand galaxies revealed hundreds of thousands under Webb's infrared vision. Faint smudges became resolved structures. Objects previously invisible emerged clearly against the background. This did not mean Hubble was wrong. It meant the universe was hiding in wavelengths human eyes cannot detect. Webb's infrared instruments revealed dusty galaxies, heavily obscured star-forming regions, and ancient systems whose light had been stretched far beyond the visible spectrum. The comparison shows that our visible light view of the universe is incomplete by design. What Webb revealed was a population of galaxies that had gone almost entirely unnoticed. These discoveries immediately created a problem. According to standard cosmological models, the early universe should have been relatively dim. The first stars ignited slowly. Galaxies grew gradually. Large amounts of light should not have existed in the first few 100 million years. Webb found the opposite. The early universe appears unexpectedly bright. Researchers measured the total light produced by galaxies in the first billion years after the Big Bang. They compared this with theoretical predictions based on known physics of star formation and structure growth. The observed light exceeded predictions by factors of several, in some cases approaching an order of magnitude. This discrepancy is now known as the too much light too early problem. It is not based on a single observation. It appears across multiple deep fields using different instruments in different parts of the sky. Something allowed the early universe to produce stars and galaxies far more efficiently than expected. Several explanations are being explored. One possibility involves how stars formed in the early universe. Modern star formation produces many small stars and relatively few massive ones. If early star formation favored larger stars, the total light output would increase dramatically. Massive stars burn hotter and brighter, even though they live shorter lives. Another possibility involves efficiency. In the modern universe, only a small fraction of available gas turns into stars. Most gas is heated, dispersed, or prevented from collapsing. Conditions in the early universe may have allowed gas to collapse more efficiently. Higher densities, more frequent collisions, and stronger gravitational interactions could have converted gas into stars at much higher rates. Black holes may also contribute. Active galactic nuclei powered by rapidly feeding supermassive black holes can outshine entire galaxies. If black holes were more active or more common in the early universe, they could account for some of the excess light. Webb has found evidence supporting this idea. Many early galaxies host extremely luminous central regions consistent with active black holes. None of these explanations fully resolves the problem on its own. What makes the situation more striking is that each new observation pushes the timeline earlier. First, bright galaxies appeared at around 600 million years. Then, at 500 million. Then, at 400 million. Now, at around 300 million years after the Big Bang. Each step reveals significant light even closer to the beginning. The standard cosmological model remains successful in many areas. It explains the cosmic microwave background. It predicts the large-scale distribution of galaxies. It accounts for the relative abundances of light elements. But it struggles with the speed at which the first structures appeared. This suggests that something about early galaxy formation is incomplete in our current understanding. the implications extend beyond brightness. If galaxies formed earlier and in greater numbers, then the universe began influencing itself sooner. Radiation from early stars would have ionized surrounding hydrogen earlier. Heavy elements would have been produced and dispersed faster. Larger structures would have assembled earlier than expected. The entire sequence of cosmic evolution may need refinement. As Webb surveys more sky, it continues to count galaxies at an unprecedented rate. If the densities observed in deep fields are representative, the total number of galaxies in the observable universe could be far higher than earlier estimates suggested. Possibly trillions rather than hundreds of billions. Each increasing galaxy count multiplies everything else. More galaxies mean more stars. More stars mean more planets. More planets mean more potential environments for chemistry and complexity. Yet even this staggering population exists only within the observable universe. Beyond the cosmic horizon lies more space, containing galaxies we will never see. Their light has not reached us, and cosmic expansion ensures that it never will. James Webb has not revealed the entire universe. It has revealed how much more exists even within what we can observe. And it has shown that the universe did not ease into existence slowly. It arrived active, luminous, and already building complexity at a pace that still challenges explanation. The challenge does not stop with galaxies. At the centers of many of these early systems sit objects that are even harder to explain. Supermassive black holes. In the modern universe, nearly every large galaxy contains a supermassive black hole at its core. These objects weigh millions or billions of times more than our Sun. They grow slowly, fed by gas, dust, and occasional stars over billions of years. In the early universe, that amount of time did not exist. Yet Webb has detected black holes of enormous mass when the universe was only a few 100 million years old. Some power quasars, the brightest continuous light sources known. A single quasar can outshine its entire host galaxy by orders of magnitude. These objects should not exist so early. Black holes form when massive stars collapse at the end of their lives. Even the largest stars produce black holes only tens of times more massive than the Sun. From there, growth is limited. Matter falling inward releases energy that pushes back against incoming material, setting a maximum growth rate. Under those limits, it should take billions of years to build a supermassive black hole. Webb sees them far sooner. In one distant galaxy, the light reveals gas moving at extreme speeds near a compact central source. The spectral signatures match those produced by matter spiraling into a massive black hole. The surrounding region glows intensely, indicating rapid accretion. This is not an isolated case. Multiple early galaxies show evidence of central black holes already weighing millions or even billions of solar masses. Their existence forces scientists to consider alternative growth paths. One possibility is that the first black holes were born massive. In the early universe, conditions were very different. Gas clouds were denser. Temperatures were higher. Heavy elements were scarce or absent. Under the right circumstances, a massive cloud of gas might collapse directly into a black hole without forming stars first. Such a direct collapse black hole could weigh tens of thousands or even hundreds of thousands of solar masses at birth. This would provide a head start, allowing rapid growth into a supermassive black hole within a few 100 million years. Another possibility involves mergers. The early universe was crowded. Galaxies were closer together. Collisions were more frequent. If smaller black holes merged repeatedly, their combined mass could increase faster than accretion alone would allow. Gravitational wave detectors have confirmed that black hole mergers occur. In the early universe, they may have been common. A third possibility involves exotic early stars. The first generation of stars formed from gas composed almost entirely of hydrogen and helium. Without heavy elements to cool the gas efficiently, these stars could grow far larger than stars formed today. Theoretical models predict stars thousands of times more massive than the Sun. These stars would burn intensely and live briefly. When they collapsed, they would form massive black holes directly. Evidence for such stars may already exist. In some distant galaxies, Webb has detected unusual chemical signatures. The ratios of certain elements do not match those produced by normal stellar populations. Instead, they match predictions for extremely massive primordial stars. If these stars existed, they would help explain both early heavy element enrichment and early black hole formation. These black holes did not exist in isolation. As they fed, they released enormous amounts of energy. Radiation from accreting black holes heats surrounding gas. This can trigger star formation in some regions while suppressing it in others. Black holes play a central role in regulating how galaxies grow. Finding them so early means they influenced cosmic evolution almost from the beginning. Beyond individual galaxies, Webb has also revealed the largest structures in the universe. Galaxies are not distributed randomly. They trace a vast network known as the cosmic web. This web consists of filaments of dark matter stretching across millions of light years. Galaxies form and move along these filaments. At intersections, matter piles up into clusters containing hundreds or thousands of galaxies. Between the filaments lie enormous voids, regions nearly empty of matter. The cosmic web emerged from tiny density variations in the early universe. Regions that were slightly denser than average pulled in more matter. Over billions of years, this process amplified, creating a network of filaments and nodes. Dark matter provides the scaffolding. It makes up the majority of all matter in the universe. It does not emit light or interact with radiation. We detect it only through its gravitational influence. Where dark matter concentrates, ordinary matter follows. Webb's observations have traced galaxies along these filaments deep into cosmic history. Some structures stretch tens of millions of light years across, even when the universe was only a few billion years old. In one striking discovery, astronomers identified a chain of galaxies aligned along a single filament. The structure extends for more than 10 million light years and contains dozens of galaxies at similar distances. Such large, organized structures were not expected so early. They appear to be the precursors of modern galaxy clusters. As time passes, galaxies drift along filaments toward these dense intersections. They collide, merge, and grow. Clusters become the largest gravitationally bound objects in existence. Webb has also helped detect dark matter directly along filaments using gravitational lensing. Light from background galaxies bends as it passes through invisible concentrations of mass. By measuring these distortions, scientists map the dark matter distribution itself. These observations confirm that the cosmic web is real, continuous, and pervasive. It connects every major structure in the observable universe. The scale of this network is difficult to grasp. Individual galaxies are separated by millions of light years. Clusters span several million light years. Filaments stretch for tens or hundreds of millions of light years. And all of it exists within an observable universe more than 90 billion light years across. Webb has shown that this structure formed earlier, faster, and more efficiently than expected. The universe did not assemble slowly from simplicity. It built complexity rapidly, on every scale, from stars to galaxies to the largest structures known. As these structures grew, they reshaped how galaxies lived and died. Galaxies do not evolve in isolation. their environment matters. When a galaxy drifts through the relatively empty regions of space, it can quietly form stars for billions of years. Gas cools slowly. New stars ignite at a measured pace. The galaxy changes gradually. But when a galaxy enters a dense region of the cosmic web, its fate can change rapidly. Galaxy clusters are extreme environments. They contain hundreds or thousands of galaxies bound together by gravity. The space between those galaxies is not empty. It is filled with extremely hot plasma, heated to tens of millions of degrees. When a galaxy falls into a cluster, it does not gently settle in. It plunges inward at tremendous speed. As it moves through the hot plasma, the galaxy experiences a force known as ram pressure. This pressure strips gas from the galaxy, peeling it away like wind tearing leaves from a tree. Long streams of gas trail behind infilling galaxies, stretching for hundreds of thousands of light years. Without gas, the galaxy loses the raw material needed to form new stars. Star formation shuts down. The galaxy becomes quiescent, filled with aging stars, but no longer producing new ones. Webb has observed many examples of this process in action. Galaxies caught mid-fall show distorted shapes, stripped gas tails, and sharply reduced star formation rates. This environmental quenching happens more efficiently in clusters than anywhere else in the universe. Smaller galaxies are especially vulnerable. Their gravity is weaker. They can lose nearly all of their gas in a single passage through a dense cluster core. Over time, these galaxies fade and redden, becoming compact remnants of their former selves. Mergers add another layer of transformation. When galaxies collide, their stars usually pass by each other without direct impact. The distances between stars are vast. But gas clouds do collide. These collisions compress gas to extreme densities, triggering intense bursts of star formation. Thousands or even millions of new stars can form in a relatively short period. Webb has captured galaxies in the act of merging, both nearby and in the early universe. Tidal forces stretch stars and gas into long arcs and streams, reshaping the galaxies involved. Major mergers between similarly sized galaxies often destroy spiral structure entirely. The result is a smooth elliptical galaxy, with stars orbiting in random directions. Gas driven toward the center during a merger can also feed the central black hole, igniting an active galactic nucleus or even a quasar. The early universe experienced mergers far more frequently than today. Galaxies were closer together. The cosmic web was more compact. Collisions were common. This likely contributed to the rapid buildup of mass seen in early galaxies. As the universe expands, mergers become less frequent. Galaxies drift farther apart. In the distant future, major mergers will be rare. Webb has also revealed how these processes affect the chemical makeup of the universe. At the beginning, the cosmos contained almost nothing but hydrogen and helium. These elements formed in the first minutes after the Big Bang. Everything heavier came later. Stars act as cosmic furnaces. In their cores, light elements fuse into heavier ones. When stars die, they release these elements into space. Each generation of stars enriches the surrounding gas. Astronomers call this enrichment metallicity. In this context, any element heavier than helium is considered a metal. Webb measures metallicity by analyzing the spectra of galaxies at different distances. Specific elements leave distinct signatures in light. By comparing these signatures, scientists determine how chemically evolved a galaxy is. The pattern is clear. The most distant galaxies show very low metallicity. They contain gas that has undergone little stellar processing. closer galaxies show progressively higher metallicity. This traces the chemical evolution of the universe across billions of years. Dense regions enrich faster. Where stars form rapidly, heavy elements accumulate quickly. Sparse regions remain chemically primitive for much longer. Mergers accelerate this process. Starbursts triggered by collisions produce large quantities of heavy elements in a short time, dispersing them widely. These elements are essential. Rocky planets require metals. Complex chemistry requires carbon, oxygen, nitrogen, and other elements forged in stars. Our own star formed from gas enriched by multiple previous generations. Every atom in the human body except hydrogen was created inside a star. Webb has shown that this enrichment began earlier and proceeded faster than expected. Even in the first billion years, some galaxies already contained significant amounts of heavy elements. This rapid chemical evolution supports the idea that the early universe was extraordinarily efficient at building complexity. Stars formed quickly. They lived and died rapidly. They seeded space with the ingredients needed for future stars, planets, and eventually life. What emerges from Webb's observations is a consistent picture. The early universe was not a quiet, empty place slowly waking up. It was dynamic, crowded, and intensely productive. Structure formed early. Stars ignited quickly. Galaxies assembled fast. Black holes grew rapidly. The cosmic web took shape sooner than expected. James Webb has not overturned cosmology, but it has exposed the limits of our current understanding. It shows us that the universe learned to build itself faster than we thought, on every scale we can observe. As Webb pushes deeper, it also sharpens a boundary that defines everything we can ever know. The observable universe is not the entire universe. It is only the region from which light has had time to reach us since the Big Bang. That boundary is called the cosmic horizon. Light has been traveling for about 13 8/10 billion years. But because space itself expands, the most distant sources we can observe today are now much farther away than that travel time alone would suggest. Those sources currently sit at a distance of roughly 46.5 billion light-years. Together, they define a sphere around us, measuring about 93 billion light-years across. Nothing beyond that boundary can ever be seen from Earth. This is not because those regions are empty. It is because space between us and them expands faster than light can cross it. Galaxies beyond the horizon emit light just as galaxies within it do. Stars shine. Supernova explode. Black holes merge. But their signals are trapped. The expansion of space stretches the gap faster than the light can close it. This creates a universe divided into regions that are permanently causally disconnected. As time passes, the horizon changes. Because expansion is accelerating, galaxies that are visible today will not remain visible forever. Their light will become increasingly stretched, shifted to longer and longer wavelengths. Eventually, it will fade beyond detectability. Far in the future, observers in our galaxy will see a much smaller universe. Only the Milky Way, Andromeda, and a handful of nearby galaxies will remain visible. Everything else will have slipped beyond the horizon. Those future observers might conclude that the universe contains only a few galaxies. The evidence for cosmic expansion, the Big Bang, and distant structure will be gone. We live at a rare moment. A moment when the universe is old enough for galaxies and stars to exist, but not yet so old that expansion has erased the record of its past. James Webb is capturing that record before it disappears. The horizon also reveals something counterintuitive about perspective. Every observer in the universe has their own observable universe. Stand anywhere in space and look out, and you will see a sphere of galaxies extending to your own cosmic horizon. That sphere depends entirely on where you are. Galaxies visible from Earth may lie beyond the horizon of an observer elsewhere. Galaxies invisible to us may be clearly visible from another location. No single observer can ever see the entire universe. There is no central vantage point, no privileged location. The universe looks roughly the same in every direction because we are not special. We occupy an ordinary position in an ordinary galaxy within an ordinary region of space. Webb reinforces this idea. It shows that the Milky Way is not unusual. It is one among countless galaxies scattered across the cosmic web. As galaxy counts increase, our sense of scale changes again. Earlier estimates suggested hundreds of billions of galaxies in the observable universe. Webb's deep fields hint at far higher numbers. If the densities seen in Webb's surveys apply broadly, the total number of galaxies could reach into the trillions. Each galaxy contains billions or trillions of stars. Each star may host planets. The resulting numbers become almost impossible to grasp. Yet even trillions of galaxies represent only what we can observe. Beyond the horizon, the universe continues. Measurements of the universe's geometry suggest that space is very close to flat. In flat geometry, parallel lines remain parallel, and space does not curve back on itself. This implies that the universe may extend indefinitely. If so, the observable universe is just one finite region within an infinite expanse. Even if the universe is finite rather than infinite, its total size would still vastly exceed what we can see. The observable sphere would remain a small subset of the whole. This raises fundamental questions about knowledge. We build theories based on observations. We test those theories using data from within the observable universe. We assume that the laws of physics apply everywhere, but we cannot test that assumption beyond the cosmic horizon. It is possible that distant regions resemble our own. It is also possible that they differ in ways we will never detect. Some models of cosmic inflation suggest that our universe may be one region among many, each with its own properties. These ideas remain speculative. They lie at the edge of what science can currently test. What Webb makes clear is this: even with our most powerful instruments, we see only a fraction of what exists. The universe is larger than our observations, richer than our catalogues, and more complex than our models yet capture. James Webb has not shown us the whole cosmos. It has shown us how much lies beyond our reach, and how much remains to be understood within the part we can see. This expanding horizon also changes how we think about time itself. Time in the universe does not pass in a single, universal way. According to relativity, time depends on motion and gravity. The faster an object moves relative to an observer, the slower its time appears to pass. The stronger the gravitational field, the more time slows. At everyday scales, these effects are negligible. At cosmic scales, they become profound. Galaxies near the edge of the observable universe appear to be receding at speeds approaching the speed of light. From our perspective, clocks in those distant galaxies appear to tick more slowly than our own. From their perspective, the opposite is true. There is no absolute frame of time. Each observer experiences time locally, while distant systems appear time-dilated. As galaxies approach the cosmic horizon, this effect becomes extreme. From our viewpoint, their evolution appears to slow dramatically. Their light becomes increasingly stretched. Eventually, it fades beyond detection. At the horizon itself, time appears to freeze. This does not mean time actually stops in those galaxies. It means the signals that would show later moments can no longer reach us. Once a galaxy crosses beyond the horizon, no future event there can ever be observed from Earth. Its history becomes permanently inaccessible. Closer regions experience far less time dilation. Galaxies in our local group are gravitationally bound and not participating in cosmic expansion at all. From our perspective, their clocks run essentially in step with ours. This creates a universe layered in time. The most distant galaxies appear as they were near the beginning. Intermediate galaxies reveal later stages of evolution. Nearby galaxies reflect something close to the present. James Webb captures this entire temporal structure in a single view. It observes galaxies separated not just by distance, but by billions of years of history. Each image compresses vast spans of cosmic time into a pattern of light. This layered time perspective is one reason Webb's discoveries are so important. They do not simply tell us what exists. They tell us when it existed, and that timing continues to challenge expectations. One of the most persistent puzzles involves how quickly stars formed in the early universe. Star formation has natural limits. Gas must cool before gravity can collapse it. Hot gas resists compression. Cooling takes time. In the modern universe, star formation is relatively inefficient. Only a small fraction of available gas becomes stars. The rest is heated, dispersed, or blown away by radiation and stellar winds. Early galaxies appear to have behaved differently. Webb has observed galaxies only a few 100 million years old, but already contain large stellar populations. Their brightness indicates rapid star formation at rates far exceeding those seen in similar galaxies today. Some early galaxies appear to convert gas into stars 10 or even 100 times more efficiently than modern systems. This raises a critical question. How did these galaxies sustain such intense star formation? Rapid star formation should exhaust gas quickly. If gas were consumed too fast, star formation would shut down almost immediately. Yet many early galaxies show evidence of sustained activity over tens of millions of years. One possible explanation involves the cosmic web itself. Simulations suggest that cold gas can stream along dark matter filaments directly into galaxies. These flows could deliver fresh material continuously, fueling star formation without requiring enormous initial gas reserves. In the dense early universe, such streams may have been especially effective. Galaxies would not rely solely on internal gas. They would be fed by their environment. This process could explain how early galaxies remain bright for extended periods despite intense star formation. It also links small-scale processes to the largest structures in the universe. The same filaments that organize galaxies across millions of light-years may have supplied the fuel that allowed those galaxies to grow rapidly. James Webb provides the observational evidence needed to test these ideas. By measuring gas content, star formation rates, and galaxy environments across cosmic time, astronomers can begin to reconstruct how efficiently matter flowed through the early universe. What is emerging is a picture of a cosmos that behaved very differently in its youth. Conditions were denser. Interactions were more frequent. Gas flows were stronger. Growth was faster. The early universe was not merely a scaled-down version of today's universe. It was a different regime altogether. And Webb is revealing that regime in unprecedented detail. This difference between the early universe and the present becomes even clearer when we look at the largest bound structures that exist. Galaxy clusters are the most massive objects gravity can hold together. They form at the intersections of cosmic web filaments, where matter accumulates over billions of years. A typical large cluster contains hundreds or thousands of galaxies. Its total mass can reach hundreds of thousands of billions of times the mass of our Sun. Most of that mass is not in stars. It is distributed as dark matter and extremely hot gas. The space between galaxies inside a cluster is filled with plasma heated to tens of millions of degrees. This gas emits X-rays and dominates the visible mass of the cluster outside of galaxies themselves. Clusters reveal the presence of dark matter directly. Galaxies inside clusters move too fast to be held together by visible matter alone. Without additional mass, clusters would fly apart. The gravitational influence of dark matter provides the binding force. Webb has observed clusters at different stages of cosmic history. Some appear mature and relaxed. Others are still assembling, drawing in galaxies along filaments of the cosmic web. By comparing clusters across time, astronomers can see how structure grows on the largest scales. In the early universe, clusters were smaller and less settled. Galaxies within them showed irregular shapes and high star formation rates. As time progressed, clusters became more massive and more organized. Star formation declined. Galaxies became smoother and redder. The influence of environment grew stronger. These observations confirm long-standing theoretical predictions. But they also reveal surprises. Some clusters appear earlier than expected. Others show levels of organization that challenge models of how quickly matter should assemble. The formation of clusters marks a turning point. Once matter collapses into a cluster, it rarely escapes. Clusters act as cosmic traps, locking galaxies into dense environments where their evolution changes permanently. Over immense spans of time, clusters will absorb surrounding galaxies. They will grow more massive. Their internal motions will slow as they settle into equilibrium. Eventually, clusters will contain fewer distinct galaxies and more diffuse stellar systems as mergers continue. But clusters are also affected by expansion. While gravity dominates inside clusters, space outside continues to stretch. Clusters remain bound islands in an increasingly empty universe. In the far future, clusters will be the last structures still holding together. Everything else will drift away. This contrast between bound structures and expanding space highlights the dual nature of cosmic evolution. On small scales, gravity wins. On large scales, expansion dominates. James Webb's observations span both regimes. It shows how stars and galaxies form and evolve under gravity. It also reveals how expansion reshapes the universe on the largest scales. Another phenomenon Webb has exploited to probe deep space is gravitational lensing. According to general relativity, mass bends space. Light traveling near massive objects follows curved paths. When a massive galaxy or cluster lies between Earth and a more distant object, it can act as a lens. The background light is bent, magnified, and distorted. In some cases, the alignment is precise enough to produce a complete ring of light around the foreground object. This is known as an Einstein ring. Einstein rings are rare, but they are powerful tools. The size and shape of a ring reveal the mass of the lensing object. This includes both visible matter and dark matter. Webb has captured some of the most detailed lensing images ever obtained. In these images, distant galaxies appear stretched into arcs and rings, magnified many times over. This magnification allows astronomers to study galaxies that would otherwise be too faint to detect. Lensing effectively turns massive galaxies and clusters into natural telescopes. Using this technique, Webb has identified some of the faintest and most distant galaxies ever observed. Objects that would be invisible even to Webb's powerful instruments become detectable when lensing amplifies their light. These observations extend our reach deeper into the early universe. They also provide direct maps of dark matter. By analyzing how light bends around lensing objects, scientists reconstruct the distribution of invisible mass. The resulting maps showed dark matter halos extending far beyond the visible boundaries of galaxies. They confirmed that dark matter dominates structure on every scale. Clusters, filaments, and even individual galaxies are embedded in massive dark matter halos. Without dark matter, the universe would look completely different. Galaxies would not form as they do. The cosmic web would not exist. Webb's lensing observations reinforce this conclusion with extraordinary clarity. They show the invisible framework that supports everything we can see. Together, these findings paint a consistent picture. The universe is structured, hierarchical, and interconnected. Small objects form first. They merge into larger ones. Those merge into larger structures still. Gravity builds upward. Expansion pulls outward. James Webb allows us to watch both processes unfold across nearly the entire history of the universe. Beyond clusters and filaments, the universe also contains regions defined by their absence. These regions are known as cosmic voids. Voids are vast volumes of space containing very little matter. They can stretch for hundreds of millions of light years in every direction. Compared to the dense nodes of the cosmic web, voids contain only a small fraction of the universe's average matter density. In some voids, fewer than 1/10 of the expected number of galaxies exist. Stars are rare. Gas is thin. Dark matter is sparse. Voids formed through the same gravitational processes that built clusters, but in reverse. Regions that began slightly less dense than average had slightly weaker gravity. Matter flowed away from them toward denser regions. As matter drained out, those regions became even emptier. Over billions of years, this process carved the universe into a pattern of dense filaments and enormous empty spaces. Voids continue to grow. As matter moves along filaments toward clusters, voids expand and merge with neighboring voids. The cosmic web becomes more pronounced, with emptier regions and denser structures. The largest known voids span close to 1 billion light-years across. Light would take nearly 1 billion years to cross from one side to the other. Standing at the center of such a void would produce a very different night sky. Galaxies would appear few and far between. Large-scale structure would be difficult to detect. Voids are scientifically valuable precisely because of their emptiness. In dense regions, gravity from nearby structures complicates measurements of cosmic expansion. Galaxies move not only because of expansion, but because of local gravitational pulls. In voids, these local effects are minimal. Galaxies move almost entirely with the expansion of space itself. This makes voids excellent laboratories for studying dark energy and cosmic expansion. By measuring how voids grow and evolve, astronomers can test cosmological models with fewer complications. So far, void statistics broadly agree with predictions from the Standard Model of Cosmology. This suggests that while some details of early structure formation need revision, the overall framework remains sound. The existence of voids also emphasizes how unevenly matter is distributed. Most of the universe's volume contains almost nothing. Most of its mass is concentrated into thin threads and dense nodes. This extreme contrast is a natural outcome of gravity acting over immense spans of time. As light travels through this uneven universe, it carries subtle signatures of the journey. Every photon from a distant galaxy is stretched by expansion. Its wavelength increases. Its energy decreases. This stretching affects not only color, but brightness. As wavelengths lengthen, energy spreads across a broader range. At the same time, expansion reduces the rate at which photons arrive. Together, these effects make distant objects appear far dimmer than their intrinsic luminosity would suggest. James Webb was designed to overcome these challenges. Its large mirror collects more light than any previous space telescope. Its detectors are sensitive enough to register photons that have been traveling for more than 13 billion years. Webb operates far from Earth, shielded from sunlight and heat. This allows it to detect faint infrared signals without interference. Even so, some of the light Webb observes is barely detectable. Deep field images often require dozens or hundreds of hours of combined exposure time. Thousands of individual observations are stacked and aligned to extract the faintest signals. The result is an image containing galaxies from nearly every epoch of cosmic history. Each pixel represents accumulated light from unimaginable distances. In some of Webb's deepest surveys, nearly 800,000 galaxies appear in a region of sky only slightly larger than a few full moons. Earlier telescopes saw only a fraction of these objects. This dramatic increase forces astronomers to revisit long-held estimates. For years, the number of galaxies in the observable universe was estimated at roughly a few hundred billion. Those estimates were based on visible light surveys and extrapolation. Webb's infrared surveys suggest the true number may be far higher. If faint galaxies are as common throughout the universe as they are in Webb's deep fields, the total population could reach into the trillions. This revision affects every calculation that depends on galaxy counts. Total stellar mass, total number of planets, the overall budget of light and energy. Each of these scales upward with the number of galaxies. The implications extend beyond astronomy. They influence how we think about probability. With more galaxies come more stars. With more stars come more planets. With more planets come more environments where chemistry can become complex. While Webb does not tell us whether life exists elsewhere, it dramatically increases the number of potential locations where it could arise. Yet even trillions of galaxies remain confined to the observable universe. Beyond the cosmic horizon, there may be vastly more. The universe does not end at the edge of what we can see. Our instruments are bounded by physics, not by the universe itself. James Webb has expanded those bounds farther than ever before. But it has also clarified a humbling truth. No matter how powerful our telescopes become, there will always be regions beyond our reach. The universe is larger than observation, larger than catalogue, and larger than certainty. This limit to what we can observe also shapes how we think about knowledge itself. Astronomy is constrained by light. Everything we know about the universe beyond our immediate surroundings comes from photons that have reached us. If light cannot arrive, information cannot arrive. This means there are events happening right now that will never influence us in any way. Entire galaxies may be forming stars, merging or collapsing into black holes beyond the cosmic horizon, completely disconnected from our region of space. From our perspective, they might as well not exist. This separation is not symmetrical in time. Some regions are currently visible but will not remain so. As expansion accelerates, their light will be stretched beyond detection. They will fade from view, not because they are destroyed, but because the space between us grows too quickly. The observable universe is therefore temporary. It is a snapshot defined by cosmic timing. James Webb is observing the universe during a narrow window when the record of its past is still accessible. That record extends back to an era when the first stars ignited. But even that view has limits. Before stars formed, the universe was dark. No visible light existed. The cosmos was filled with neutral hydrogen gas that absorbed radiation. This period is known as the Cosmic Dark Ages. Eventually, the first luminous objects appeared. Their radiation began ionizing the surrounding hydrogen, making the universe transparent to light. This transition is called re-ionization. ionization. Understanding when and how reionization occurred is one of Webb's key scientific goals. By studying galaxies at different distances, Webb traces how the fraction of ionized gas changed over time. Early results suggest reionization began earlier and proceeded more quickly than previously thought. Small galaxies may have played a major role. While large galaxies are bright, small galaxies are far more numerous. Even if each produces modest amounts of radiation, their combined output can dominate. Webb's sensitivity allows it to detect these faint systems for the first time. By counting them and measuring their properties, astronomers can estimate how much ionizing radiation they produced. This helps reconstruct how the universe transitioned from darkness to light. The timing of reionization matters. It affects how early galaxies formed. It influences how gas cooled and collapsed. It shapes the growth of later structures. Webb's observations indicate that galaxies were already numerous and active when reionization was underway. This reinforces the picture of a highly productive early universe. The same galaxies responsible for reionization also contributed to chemical enrichment. As stars lived and died, they produced heavier elements and dispersed them into space. These elements altered the behavior of gas, enabling new cooling pathways and changing how future stars formed. In this way, the first galaxies set the conditions for everything that followed. They transformed the universe from a simple mixture of hydrogen and helium into a chemically complex environment capable of forming planets. James Webb allows astronomers to connect these processes across time. By observing galaxies before, during, and after reionization, scientists can track how light, matter, and structure interacted. This is not a simple linear story. Different regions evolved at different rates. Dense areas lit up first. Sparse regions lagged behind. The universe did not reionize all at once. It happened in patches, driven by clusters of early galaxies. Webb's wide surveys reveal this patchwork directly. Some regions show evidence of early transparency. Others remain partially neutral at the same cosmic time. This unevenness is another sign that the early universe was not uniform in its behavior. Gravity, environment, and feedback all played roles. As Webb continues to observe, it refines this timeline. Each new deep field adds data points. Each spectrum improves distance estimates. Each faint galaxy fills in another piece of the puzzle. What emerges is a universe that transitioned from darkness to light rapidly, driven by an unexpectedly large population of early galaxies. This again points to the same conclusion. The universe formed structure earlier and faster than predicted, and that rapid beginning echoes through everything we see today. As these early processes unfolded, they left lasting signatures that Webb can still detect today. One of the most important is chemical imbalance. Not all elements are produced in equal amounts or on the same timescales. Massive stars live fast and die young. They create large amounts of oxygen, carbon, and other light-heavy elements. Smaller stars live longer and produce iron and heavier elements much later. Because of this, the ratio of elements inside a galaxy reveals its history. Webb has measured these ratios in some of the most distant galaxies ever observed. The results show extreme imbalances that cannot be explained by normal stellar populations alone. In several early galaxies, nitrogen appears far more abundant than expected compared to oxygen. This pattern does not match what ordinary stars produce. However, theoretical models predict exactly this signature from an unusual class of objects: extremely massive primordial stars. These stars would have formed from nearly pure hydrogen and helium before heavy elements were common. Without metals to help cool gas clouds, the first stars could grow extraordinarily large. models suggest masses reaching thousands of times the mass of our Sun. Such stars would burn at extreme temperatures. Inside their cores, nuclear reactions would rapidly convert helium into carbon. That carbon would then participate in processes that generate large amounts of nitrogen. These stars would live only a few million years. They would not explode as typical supernova. Instead, they would collapse directly into massive black holes. During their short lives, powerful stellar winds would eject nitrogen-rich material into surrounding space. Webb's observations match this prediction. The chemical fingerprints seen in some early galaxies are consistent with enrichment from these primordial giant stars. If confirmed, this represents the first direct observational evidence that such stars actually existed. For decades, they were theoretical constructs. They were expected, but never seen. Their existence helps resolve multiple puzzles at once. They explain how heavy elements appeared so early. They provide seeds for the rapid growth of supermassive black holes. They contribute large amounts of ultraviolet radiation that would accelerate reionization. In other words, they help explain why the early universe appears far more active than expected. These primordial stars did not last. They were transitional objects, existing only in the earliest cosmic era. As heavy elements accumulated, gas behavior changed. Star formation shifted towards smaller, longer-lived stars, like those that dominate today. But the impact of those first stars remained. They altered the chemistry of the universe permanently. Every later generation of stars formed from gas they had enriched. James Webb allows astronomers to glimpse this transition directly. By comparing galaxies across redshift, scientists can see how chemical signatures evolve. Early systems show extreme, unbalanced ratios. Later systems gradually resemble modern galaxies. This confirms that the universe underwent a rapid chemical maturation. Complexity arrived quickly. The same early stars that enriched space also influenced how galaxies interacted with their surroundings. Radiation from massive stars heats nearby gas. It can prevent further star formation locally while triggering it farther away. This feedback shapes galaxy growth. In the dense, early universe, feedback effects were likely intense. Galaxies were small, gas-rich, and closely packed. Energy released by stars and black holes could escape more easily, affecting large volumes of space. This may explain why some early galaxies show abrupt shutdowns in star formation. They burned bright, then faded quickly. Others continued forming stars, sustained by inflows of fresh gas from the cosmic web. Webb's observations show both outcomes. Some early galaxies appear actively forming stars. Others already look quiescent despite their youth. This diversity was not expected. It suggests that environment and feedback played major roles even at the beginning. The universe did not follow a single developmental path. It explored many. James Webb is revealing that complexity was present from the start, not only in structure and chemistry, but in behavior. This early diversity becomes even more striking when we look at how galaxies shut down star formation. In the modern universe, galaxies typically fade slowly. Gas is used up over billions of years. Star formation declines gradually. In the early universe, Webb shows that this process could happen far faster. Some galaxies only a few 100 million years old already appear quiescent. Their spectra show little evidence of ongoing star formation. They are dominated by older stellar populations despite their young cosmic age. This is unexpected. There should not have been enough time for these galaxies to form stars rapidly and then shut down so completely. Several mechanisms may explain this rapid quenching. One involves mergers. When galaxies collide, star formation can spike dramatically. Gas is compressed. Stars form in bursts. But this intense activity can exhaust available gas quickly. The same collisions can also drive gas toward the central black hole. As the black hole feeds, it releases enormous energy. That energy heats surrounding gas or expels it entirely. Without cold gas, star formation stops. Another mechanism involves environment. Galaxies embedded in dense regions experience stronger interactions with their surroundings. They may lose gas through tidal forces or pressure from surrounding plasma even at early times. In the crowded early universe, these effects could act quickly. Webb's observations suggest that quenching occurred through multiple pathways. Some galaxies burned fast and died young. Others continued forming stars for longer periods. This reinforces the idea that early galaxy evolution was not uniform. Different regions followed different trajectories depending on local conditions. As galaxies quenched, their light changed. Young, massive stars burn hot and blue. Older stars glow redder and cooler. As star formation shuts down, a galaxy's overall color shifts. Webb's infrared instruments detect this change even at extreme distances. By measuring galaxy colors and spectra, astronomers reconstruct star formation histories across cosmic time. These measurements show that the transition from active to quiescent happened earlier than expected. Again, the theme repeats. The universe moved quickly. The same speed appears in the growth of black holes. Some early galaxies show evidence that their central black holes grew rapidly and then entered quieter phases. This suggests cycles of activity and dormancy occurred very early. Black holes did not simply grow steadily. They likely grew in bursts, shaped by mergers and gas inflows. Webb's data supports this picture. Spectral signatures reveal periods of intense accretion followed by quieter intervals. These cycles influence galaxy evolution. During active phases, black holes regulate star formation through feedback. During quiet phases, galaxies can recover if fresh gas arrives. The balance between these phases shapes galaxy growth. This balance appears to have been established early. Beyond individual galaxies, Webb also sheds light on how galaxy populations evolved as a whole. By surveying large areas of sky at different depths, astronomers can count galaxies at different epochs. These counts reveal how the number of galaxies changed over time. Surprisingly, the number of galaxies rises sharply at early times. Then, it plateaus. This suggests that many galaxies formed early and then merged into larger systems. Rather than a steady creation of new galaxies, the universe experienced a rapid initial buildup, followed by consolidation. Small systems formed first. They merged into larger galaxies. Those larger galaxies continued evolving internally. This hierarchical growth matches theoretical expectations, but the speed still challenges models. The universe did not take its time. It built a crowded, complex cosmos quickly. James Webb's observations consistently point to the same conclusion. The early universe was efficient, dynamic, and surprisingly mature. And every new dataset reinforces that message. This rapid buildup also reshapes how we interpret the universe's overall timeline. For much of modern cosmology, the early universe was imagined as a long prelude, a slow emergence from simplicity into complexity. Stars first, then small galaxies. Then, much later, large structures. James Webb is revising that picture. Instead of a long, quiet opening act, the universe appears to have entered a period of intense activity very quickly. Within a few 100 million years, Stars were forming at high rates. Galaxies were assembling. Black holes were already influencing their environments. This does not mean the Big Bang model is wrong. The universe is still about 13 8/10 billion years old. The cosmic microwave background still records its earliest conditions. What has changed is our understanding of how fast complexity emerged. Gravity acted efficiently. Gas collapsed rapidly. Feedback processes operated early. The universe learned to organize itself sooner than expected. This has consequences for how we interpret cosmic milestones. The era of cosmic dawn may have been shorter than previously thought. The transition from darkness to light may have overlapped strongly with early galaxy growth. Rather than a clean sequence of stages, early cosmic history may have been messy and overlapping. James Webb's observations suggest that multiple processes were happening at once. Star formation, chemical enrichment, black hole growth, and reionization progressed together. This interconnectedness helps explain why so many early observations appear surprising when considered in isolation. Viewed together, they form a consistent picture of an early universe operating in a high-intensity mode. This picture also helps explain why some theoretical models struggle. Many models assume average conditions and gradual change. The early universe was neither average nor gradual. It was dense. It was turbulent. It was crowded. Under those conditions, processes that are slow today could have proceeded much faster. Webb is providing the data needed to refine these models. By measuring star formation rates, gas content, metallicity, and environment simultaneously, astronomers can test how these factors interacted. This will likely lead to revisions rather than replacements. The foundations of cosmology remain strong, but the details are evolving. Beyond physics, there is also a deeper implication. The universe we see today carries the imprint of its rapid beginning. The distribution of galaxies, the structure of the cosmic web, the abundance of heavy elements, the existence of planets. All of these trace back to decisions made in the universe's first few 100 million years. James Webb allows us to observe those decisions directly. It shows us not just where galaxies are, but how they came to be. And as Webb continues to observe, it will keep pushing our understanding closer to the beginning. There are still regions of parameter space unexplored. Still faint populations waiting to be detected. Still physical processes not fully constrained. Future observations will refine distances. They will clarify chemical signatures. They will improve counts of the faintest galaxies. Each improvement will sharpen the picture. But the central lesson is already clear. The universe is larger than we imagined. It is more crowded than we expected. And it became complex far earlier than our theories predicted. James Webb has not merely extended our vision. It has expanded our perspective. It shows us a universe that does not ease into existence. It arrives quickly, builds rapidly, and fills space with structure almost from the start. That realization changes how we think about everything that followed. From the formation of galaxies, to the creation of stars, to the emergence of planets, and ultimately to the conditions that allowed life to arise at all. One of the most persistent challenges raised by these observations involves the expansion rate of the universe itself. The universe is expanding. This has been known for nearly a century. Galaxies, on average, are moving away from one another, carried apart by the stretching of space. The rate of that expansion is described by a value called the Hubble constant. It tells us how fast galaxies recede as a function of distance. For many years, scientists expected that as measurements improved, this value would converge toward a single precise number. Instead, it has split. When astronomers measure the expansion rate using the early universe, they get one answer. When they measure it using the nearby universe, they get another. This discrepancy is known as the Hubble tension. One approach looks back to the cosmic microwave background. This faint radiation is the afterglow of the Big Bang, released when the universe was only a few 100,000 years old. Its tiny temperature variations encode information about the universe's contents and expansion history. From this data, scientists infer a present-day expansion rate of roughly 67 kilometers per second per megaparsec. Another approach measures the nearby universe directly. Astronomers observe Cepheid variable stars and type ER supernova in relatively close galaxies. These objects have known intrinsic brightness, allowing accurate distance measurements. Combining those distances with redshift measurements produces a higher expansion rate, closer to 73 kilometers per second per megaparsec. The difference is small in absolute terms, but large statistically. Both methods are precise. Both have been tested repeatedly. Neither appears to contain an obvious error large enough to explain the discrepancy. James Webb has played a crucial role here. One possibility was that earlier measurements of nearby distances were biased by unresolved stars or dust. Webb's sharper infrared vision allows astronomers to resolve individual stars more clearly and see through dust more effectively. Using Webb, teams remeasured distances to galaxies hosting supernova using multiple independent methods. The results confirmed the higher expansion rate. This ruled out the idea that the discrepancy was caused by measurement error in earlier observations. The tension remains. This creates a profound puzzle. If our understanding of the early universe is correct, the expansion rate today should match what we observe locally. If our local measurements are correct, then something about the universe's evolution is missing from current models. Several explanations are being explored. One possibility is that dark energy is not perfectly constant. Its strength may have evolved slightly over cosmic time. Even small changes could affect the expansion history enough to create the observed tension. Another possibility involves additional components in the early universe. Unknown forms of energy or particles could have influenced expansion before recombination, leaving subtle imprints in the cosmic microwave background. Some models introduce early dark energy that briefly altered expansion before fading away. Others consider new interactions involving neutrinos or dark matter. At present, none of these explanations has been confirmed. What makes the Hubble tension especially important is that it affects everything. The universe's age, its size, its fate, all depend on how expansion behaves. James Webb does not solve this problem on its own, but it sharpens it. By confirming measurements on both sides of the tension, Webb has made it clear that the discrepancy is real. This suggests that the standard model of cosmology, while extremely successful, may be incomplete, not wrong in its foundations, but missing a subtle piece of physics. This would not be unprecedented. In the past, unexplained discrepancies have often led to major discoveries. The orbit of Mercury led to general relativity. Missing mass in galaxies led to dark matter. Accelerating expansion led to dark energy. The Hubble tension may point toward the next revision. And once again, it connects back to the early universe. If expansion behaved differently when the first stars and galaxies formed, it could help explain why structure appeared so quickly. Faster early expansion could alter how matter clumped. Additional energy components could influence how efficiently galaxies assembled. In this way, puzzles that initially appear separate may be related. James Webb is revealing that the early universe was not only active, but also finely balanced. Small changes in physics could have large consequences. Understanding those changes may be key to resolving several of the mysteries Webb has uncovered. As these measurements accumulate, they are forcing scientists to reconsider how tightly the universe's history is constrained. For a long time, cosmology rested on a small set of parameters: a single expansion rate, a fixed amount of dark matter, a constant dark energy density. Within this framework, the universe evolved predictably. James Webb is showing that reality may be more nuanced. The early universe appears unusually productive. Structure formed rapidly. Light appeared sooner. Massive objects emerged earlier than expected. At the same time, expansion measurements resist unification. These two facts may be connected. If expansion behaved slightly differently in the early universe, it could change how quickly matter collapsed into stars and galaxies. Even modest deviations in expansion rate affect density. Density affects gravity. Gravity determines how efficiently structure forms. A denser early universe allows gas to collapse more readily. Star formation accelerates. Black hole growth speeds up. This could help explain why Webb finds galaxies that seem too massive, too bright, and too mature for their age. Some theoretical models explore this possibility. In these models, the universe briefly experienced an additional energy component early on. This component altered expansion for a limited time, then faded. The overall age of the universe remained similar, but the timing of key events shifts. Structure formation advances. Reionization begins earlier. Black hole seeds grow faster. These ideas remain speculative, but they are testable. James Webb provides the observations needed to test them. By mapping galaxy populations across many epochs, scientists can see whether changes in expansion history match observed trends. If models with early deviations reproduce Webb's data better than standard models, they gain credibility. If not, they are ruled out. This is how cosmology progresses. Observation constrains theory. Theory predicts new observations. The cycle repeats. Webb has dramatically expanded the observational side of this process. It has also highlighted another subtle effect of expansion. Expansion does not only stretch space, it stretches time. When astronomers observe distant galaxies, they are not seeing them evolve at normal speed. Cosmic time dilation slows observed processes. A galaxy observed at high redshift appears to evolve more slowly from our perspective. Events inside it are stretched out in time. This is a direct consequence of expansion. If light wavelengths are stretched, so are time intervals. An event that lasted 1 million years in the galaxy's own frame appears to last several million years when observed from Earth, depending on distance. This effect must be accounted for when interpreting star formation histories and black hole growth. James Webb's data incorporates these corrections carefully. Even after accounting for time dilation, early galaxies still appear unusually active. Their intrinsic star formation rates remain high. Their black holes still grow rapidly. This reinforces the conclusion that the early universe itself behaved differently. Another insight from Webb concerns how galaxies interacted with their surroundings. Early galaxies did not evolve in isolation. They were embedded in dense environments where gas flowed continuously along cosmic filaments. Simulations show that cold gas streams could feed galaxies directly, bypassing shock heating that limits growth today. This mode of growth is far less efficient in the modern universe. Space has expanded. Gas densities have dropped. Streams are weaker and less continuous. In the early universe, these streams may have delivered vast amounts of fuel directly into galaxy centers. This would sustain rapid star formation without exhausting local gas reserves. Webb's observations support this picture. Some early galaxies show signs of sustained activity rather than brief bursts. Their stellar populations indicate continuous formation over tens of millions of years. This requires a steady fuel supply. Cosmic filaments provide a natural explanation. Once again, the cosmic web emerges as a central player. It does not merely organize galaxies spatially. It regulates how they grow. Where filaments intersect, galaxies thrive. Where they are isolated, growth slows. James Webb's deep fields reveal this pattern even at extreme distances. The earliest galaxies already trace the web's structure. This means the web formed very early. Dark matter collapsed quickly. Baryonic matter followed. The scaffolding of the universe was in place sooner than expected. All of this feeds into a larger realization. The universe is not only larger than we thought, it is more interconnected. Events in one region influence others through gravity, radiation, and gas flows. Early galaxies shaped their environments. Their environments shaped them in return. James Webb is revealing this feedback in action across cosmic time. As observations continue, patterns that once seemed anomalous begin to align. Early brightness, rapid growth, unexpected maturity. They may all be symptoms of the same underlying conditions. A universe that started dense, energetic, and highly efficient. Understanding that beginning is essential, because everything that exists now traces back to it. As this picture comes into focus, it becomes clear that scale is not just a matter of distance. It is also a matter of accumulation. The universe did not simply expand outward. It layered complexity on top of itself. Small differences early on produced enormous differences later. Tiny fluctuations in density became galaxies. Galaxies gathered into groups. Groups merged into clusters. Clusters traced the filaments of the cosmic web. Each step amplified what came before. James Webb shows that this amplification began almost immediately. The first stars did not merely flicker into existence. They ignited feedback loops. Their radiation heated gas. Their winds reshaped surroundings. Their deaths seeded space with heavy elements. Those elements changed how the next generation of stars formed. This chain reaction accelerated cosmic evolution. It explains why the universe did not remain simple for long. Even the smallest early galaxies were already altering their environments. Radiation escaped into intergalactic space. Ionized bubbles expanded. Chemical enrichment spread outward. By the time the universe was only a few 100 million years old, these effects overlapped. The cosmos became interconnected far earlier than expected. James Webb's observations make this visible. Galaxies are not isolated points. They exist in context. Their properties correlate with environment. Their histories intertwine. This interconnectedness also extends to black holes. Black holes do not grow independently of galaxies. Their growth depends on gas supply. Gas supply depends on environment. Webb shows that early black holes were embedded in gas-rich systems fed by cosmic filaments. This provided the fuel needed for rapid growth. At the same time, energy released by accretion influenced the surrounding galaxy. Gas could be heated or expelled. Star formation could be regulated or shut down. These feedback loops appear to have operated almost from the beginning. This challenges earlier assumptions that black hole feedback became important only later. Instead, Webb suggests it played a role very early in shaping galaxies. This helps explain why some young galaxies already appear quenched. They may have shut themselves down. Another aspect of scale Webb reveals involves visibility itself. Not all galaxies are equally easy to see. Brightness depends on mass, star formation rate, dust content, and age. Earlier surveys favored bright, massive systems. Webb uncovers a hidden majority: faint galaxies, low-mass systems, objects that contribute little individually but dominate collectively. These faint populations matter. They shape reionization. They contribute to total stellar mass. They influence chemical enrichment. Ignoring them leads to incomplete conclusions. Webb corrects that bias. It reveals that the universe's early population was dominated by small systems. Large galaxies existed, but they were rare. Most structure formed bottom up. Small objects first, large ones later. This matches hierarchical theory, but again, the timing is compressed. Everything happened sooner. The implications extend to planet formation. Heavy elements appeared early. Dust formed quickly. The raw materials for planets existed sooner than expected. This does not mean planets formed immediately, but it means the conditions required for planet formation arose early. By the time the universe was a few billion years old, many galaxies already contained enriched gas. From that gas, planetary systems could emerge. James Webb has even begun probing protoplanetary disks in nearby regions, revealing how dust grains grow and organize. While these observations focus on the local universe, they connect directly to early chemical enrichment. Without the first generations of stars, none of this would be possible. The universe had to build complexity before it could host planets. Webb shows that it wasted little time doing so. This also reframes how we think about rarity. If galaxies formed early and abundantly, then stars did too. If stars formed early, then opportunities for planetary systems multiplied. The universe may have been capable of producing habitable environments far earlier than once assumed. Whether life actually emerged early is unknown. But the window of possibility opened sooner. At the same time, expansion was working against connection. As space stretched, regions became isolated. The same expansion that allowed structure to grow also ensured eventual separation. This creates a cosmic tension: growth versus isolation, connection versus loss. James Webb captures the universe near the peak of its visibility. We can still see far back in time. We can still observe a rich cosmic web. In the far future, much of this information will be inaccessible. Galaxies will fade beyond detection. The cosmic microwave background will redshift away. Future observers may see a quiet, empty universe. They will not know the richness that once existed. We are living during a privileged epoch, not because the universe is special now, but because its history is still observable. James Webb extends that privilege. It allows us to see nearly to the beginning. It shows us that the universe was never simple for long. It grew fast. It grew crowded. It grew complex. And it continues to expand beyond our reach. This perspective also reframes how we think about disappearance. Galaxies are not vanishing because they are destroyed. They are vanishing because space itself is pulling them away. As cosmic expansion accelerates, distant galaxies move outward faster and faster. Eventually, their light becomes stretched beyond detectability. First, their visible light shifts into infrared, then into far infrared, then into wavelengths too long for any telescope to observe. At that point, those galaxies effectively fade from the observable universe. They still exist. They still shine in their own regions of space, but no information from them can reach us. This process is already underway. Galaxies at extreme distances are dimmer not only because they are far away, but because expansion dilutes their light. James Webb allows us to see many of these galaxies just before they slip beyond reach. It captures them at the edge of observability. In doing so, it preserves a record that will not always be accessible. This adds urgency to its mission. Every deep field is a snapshot of a universe that is gradually erasing its own past. The farther we look, the closer we come to that erasure boundary. This boundary is not fixed. It grows outward as time passes, but space grows faster. New regions enter the observable universe briefly, then leave again as expansion accelerates. The net effect is a slow loss of information. Over trillions of years, the observable universe will shrink in practice, even as space continues to expand. This future is dictated by dark energy. If dark energy remains constant, expansion will continue accelerating indefinitely. Galaxy clusters will remain bound, but everything beyond them will drift away. The night sky will empty. This does not affect the physics of local systems. Stars will continue to form inside galaxies for some time. Planets will orbit. Black holes will merge. But the larger cosmic context will disappear. Future astronomers, if any exist, will face a very different universe. They will not see the cosmic microwave background. They will not see distant galaxies. They will not be able to reconstruct cosmic history. James Webb operates before that curtain closes. It allows us to map the universe while its structure is still visible. This also emphasizes how contingent knowledge can be. Our understanding of the universe depends on when we exist. We happen to live at a time when evidence from the early universe is still observable. That evidence will not always be available. James Webb extends this window, but it cannot make it permanent. Another implication of scale concerns causality. There are regions of space so distant that no signal from them will ever reach us. They are causally disconnected. Events happening there cannot influence us. Likewise, events here cannot influence them. This divides the universe into countless separate observational domains. Each observer sees their own cosmic horizon. From any given location, there is a sphere of space that can be observed. Beyond that sphere lies more universe, inaccessible and unknowable from that vantage point. This means there is no single observable universe. There are many. Each observer occupies the center of their own. James Webb reveals our particular observable domain in extraordinary detail. But it also reminds us that it is only one slice of a much larger reality. What lies beyond cannot be mapped directly. We infer its existence from symmetry, uniformity, and theory. The universe appears similar in every direction we can observe. This suggests it continues beyond our horizon in the same way. But this remains an inference. We cannot test it directly. This limitation is fundamental, not technological. No telescope can overcome it. James Webb brings us closer to that boundary than ever before. It does not cross it. And yet, within that boundary, it has revealed far more than expected. More galaxies, more light, more structure, more complexity. The universe is not only larger in extent, it is richer in content. Each new observation increases the inventory of what exists. Each revision pushes numbers upward. This trend may continue. As Webb surveys more regions, counts may rise further. As analysis improves, faint populations may multiply. The universe may contain far more than we currently estimate. Even the current numbers strain comprehension. Trillions of galaxies, each with billions or trillions of stars. Each star potentially hosting planets. The scale exceeds intuitive understanding. It forces a shift in perspective. Earth is not central. Our galaxy is not special. Our region is not privileged. We are part of a vast, typical universe. James Webb confirms this with clarity. It shows that wherever we look, complexity appears. There are no favored directions, no edges, no signs of uniqueness. The same processes operate everywhere. Gravity, expansion, radiation, chemistry. This uniformity suggests deep simplicity beneath apparent complexity. The laws of physics apply universally. They produce diversity through repetition and scale. James Webb reveals the outcome of that process. A universe that builds structure rapidly, spreads it widely, and then slowly pulls it apart. A universe that creates opportunity early and then limits connection later. This dual nature defines cosmic history. Growth followed by isolation. Visibility followed by loss. We exist during the transition. And James Webb allows us to witness it. Seen this way, the universe's story is not one of steady revelation, but of narrowing opportunity. There was a time when the universe was opaque, then a time when it became transparent. Now there is a time when it is slowly becoming unreachable again. James Webb sits precisely in that middle era. It observes a universe that has already formed structure but has not yet erased its own record. This makes its discoveries uniquely valuable. Many of the galaxies Webb detects will never be observable again by any future civilization, no matter how advanced. Their light is arriving now or not at all. As expansion accelerates, the cosmic horizon tightens its grip. The universe does not hide information maliciously. It simply stretches space. Information thins, wavelengths lengthen, arrival rates slow. Eventually, signals fall below detectability. This is not failure of instrumentation. It is the geometry of space-time itself. James Webb works at the edge of this geometry. It captures photons that have crossed nearly the entire observable universe. Each one carries an imprint of conditions that no longer exist: temperature, density, chemical composition. These photons are fossils, preserved not in stone, but in motion. The deeper Webb looks, the older the record becomes. At the greatest distances, the universe appears raw. Stars are young. Galaxies are irregular. Chemical complexity is limited. Yet even there, Webb finds organization. Structure exists earlier than expected. Patterns emerge quickly. This tells us something fundamental. Order does not require long time spans to arise. Under the right conditions, complexity forms rapidly. The early universe was such a condition. Dense, energetic, highly connected. Matter flowed freely along filaments. Radiation escaped efficiently. Feedback loops activated early. This environment favored rapid growth. James Webb's discoveries are not isolated anomalies. They are consistent across fields, surveys, and methods. Different teams, different instruments, different analysis techniques. The same conclusion appears repeatedly. The early universe was busy. This consistency is important. It means the surprises are not statistical flukes. They reflect underlying reality. When theory and observation diverge systematically, theory must adapt. That adaptation is already underway. Cosmological simulations are being revised. Star formation prescriptions are being updated. Black hole seed models are being reconsidered. Early feedback mechanisms are being re-examined. None of this discards existing physics. Instead, it refines how known processes behaved under extreme conditions. The universe did not break the rules. It exploited them efficiently. This efficiency may be the key. Many processes that seem slow today were faster when the universe was smaller. Distances were shorter. Densities were higher. Cooling times differed. Under those conditions, gas collapsed more readily. Stars ignited faster. Mergers occurred more frequently. James Webb is showing us that context matters. Physics does not operate in isolation from environment. The same laws can produce very different outcomes depending on conditions. This insight extends beyond cosmology. It is a general principle of complex systems. Small changes early lead to large differences later. In the universe's case, those early differences shaped everything that followed. The distribution of galaxies, the abundance of elements, the formation of planets. Even the possibility of life traces back to early efficiency. Without rapid enrichment, rocky worlds would be rare. Without early structure, galaxies might never stabilize. Without early feedback, runaway growth could dominate. The universe found a balance quickly. James Webb is revealing that balance in action. At the same time, Webb highlights the limits of extrapolation. We are tempted to assume that what we see nearby applies everywhere and everywhen. The early universe reminds us that this is not always true. Conditions change. Outcomes change. Modern galaxies are not perfect analogues of early ones. Modern star formation is not identical to primordial star formation. Modern black hole growth is not representative of early growth. Webb allows us to observe these differences directly. It shows evolution, not just endpoints. This is perhaps its greatest contribution. Not simply deeper images, but continuity. A connected narrative stretching from the first stars to the present day. Each observation slots into a larger timeline. As this timeline fills in, the universe's scale becomes more meaningful. Not just how big it is, but how it became so structured. Not just how many galaxies exist, but why they exist in that form. James Webb turns scale into story. A story that begins quickly, unfolds densely, and then slowly disperses. And we are reading it while it is still legible. Seen from this perspective, the universe's scale is not only a question of distance, but of access. What we are able to observe depends entirely on how light has moved through expanding space. Every observation is constrained by causality, by the finite speed of light, and by the accelerating expansion driven by dark energy. James Webb operates at the edge of these constraints, gathering photons that have traveled for nearly the entire history of the universe. Those photons represent conditions that no longer exist, environments that have long since transformed or vanished beyond reach. As expansion accelerates, the universe gradually hides its own past. Distant galaxies do not disappear suddenly. Instead, their light stretches, thins, and fades. Wavelengths lengthen until they fall outside detectable ranges. Photon arrival rates slow until signals blend into noise. Eventually, no conceivable telescope can retrieve that information. This loss is not due to technological limitation, but to the geometry of space-time itself. Webb captures the universe during a fleeting era when that record is still accessible. This has profound implications for cosmology. The observable universe is not a fixed entity. It is a time-dependent boundary defined by expansion history. Regions that are visible now may not remain so indefinitely. Conversely, some regions were once visible in the past, but are no longer accessible today. The observable universe is a moving window, not a permanent map. James Webb extends that window deeper than ever before, but it cannot stop it from shifting. Within this window, Webb reveals a universe that is far more densely populated than previously assumed. Deep field surveys show that what once appeared as empty darkness is filled with faint galaxies. These systems are small, low mass, and individually dim, but collectively dominant. Their abundance reshapes estimates of total stellar mass, total light production, and the timing of key cosmic transitions such as reionization. The early universe was not sparsely populated with a few bright galaxies. It was crowded with countless faint ones, forming stars, emitting radiation, and shaping their surroundings. This realization helps explain several long-standing puzzles. Reionization, for example, required enormous amounts of ultraviolet radiation to ionize hydrogen throughout intergalactic space. Bright galaxies alone could not supply enough photons. The newly revealed population of faint galaxies changes that calculation entirely. While each contributes modestly, their combined output becomes sufficient. Webb's data suggests that reionization was driven not by rare giants, but by a vast population of small systems acting together. The same population also contributes to chemical enrichment. Heavy elements appear earlier than expected because star formation was widespread. Even small galaxies hosted massive stars that lived briefly and died explosively, dispersing carbon, oxygen, and nitrogen into surrounding gas. This rapid enrichment altered how subsequent generations of stars formed, accelerating the transition from primordial simplicity to chemical complexity. Webb's spectroscopy shows this progression clearly, with elemental ratios evolving steadily across redshift. At the same time, Webb reveals that this early universe was not uniform in behavior. Some galaxies formed stars continuously, sustained by gas inflows along cosmic filaments. Others experienced intense bursts, followed by rapid quenching. Environment played a decisive role. Dense regions promoted mergers and accelerated evolution. Sparse regions evolved more slowly. This diversity existed almost from the beginning, challenging earlier views that early galaxies followed a single developmental path. Black holes add another layer to this picture. Webb's observations show that supermassive black holes were already active when the universe was only a few 100 million years old. Their growth rates exceed what standard models predict if black holes form only from the remnants of normal stars. This has renewed interest in alternative seed mechanisms, including direct collapse scenarios and the remnants of extremely massive primordial stars. The presence of such black holes so early suggests that feedback between black holes and galaxies began shaping evolution almost immediately. These feedback processes influence star formation, gas retention, and galaxy morphology. Energy released by accreting black holes can heat surrounding gas or drive it out entirely, shutting down further star formation. Webb's data indicates that some young galaxies already show signs of such regulation. This means that the mechanisms governing galaxy growth today were already operating near the cosmic dawn. All of this reinforces a central theme. The early universe was not a slow, tentative beginning. It was a period of intense activity, rapid structure formation, and efficient use of available matter. Gravity acted quickly. Gas flowed freely. Radiation escaped widely. Complexity emerged fast. James Webb is not revealing exceptions to this pattern. It is revealing the pattern itself. This understanding reframes how we interpret cosmic scale. The universe is not merely large in extent. It is large in content. Every revision driven by Webb increases counts, densities, and totals. More galaxies than expected, more stars than assumed, more planets than previously imagined. The observable universe, spanning 93 billion light-years across, contains staggering richness. And this is only the portion we can see. Beyond the observable boundary, space almost certainly continues. The uniformity of the cosmic microwave background and the large-scale distribution of galaxies suggest no nearby edge. Whether the universe is finite or infinite remains unknown, but either case implies vastly more structure beyond our horizon. Entire regions of space exist that are causally disconnected from us. Their events cannot influence us. Our events cannot influence them. Each region possesses its own observable universe, defined by its own horizon. James Webb shows us our version of that universe with unprecedented clarity. But it also reminds us that it is only one perspective among many. From another location, the observable sphere would be different. Galaxies we see would lie beyond reach. Galaxies invisible to us would dominate the sky. No single vantage point captures the whole. This realization does not diminish our place. It contextualizes it. We are not central, but we are not insignificant. We exist at a time when the universe's history is still readable, when light from the first galaxies is still arriving, when cosmic structure is still visible across vast distances. This is a temporary privilege, granted by timing rather than position. James Webb extends that privilege. It allows us to read further back, see more clearly, and understand more deeply. It shows that the universe became complex early, expanded relentlessly, and now slowly hides its past. In doing so, it transforms scale from abstraction into narrative. A universe that ignites quickly, organizes efficiently, and then gradually drifts apart. At the largest scales, the universe reveals a strange balance between abundance and isolation. James Webb shows a cosmos overflowing with structure, yet fundamentally fragmented by expansion. Galaxies form in immense numbers, stars ignite by the trillions, planets likely number beyond comprehension, and yet the distances between these systems impose hard limits on connection. The same expansion that allowed galaxies to form also ensures that most of them will never interact, communicate, or influence one another. Space grows faster than light can cross it. Regions drift beyond causal contact, becoming permanently isolated despite sharing the same cosmic origin. This isolation reshapes how we think about existence within the universe. Each location defines its own observable domain, a sphere bounded by the distance light has had time to travel since the beginning. Beyond that sphere, reality continues, but information does not arrive. Two galaxies separated by enough distance may both be visible from Earth while remaining invisible to each other. From their perspectives, each occupies the center of its own observable universe. There is no universal vantage point, no location from which the whole can be seen. The universe has no center in space, only countless centers of observation. James Webb highlights this truth by mapping our observable region in extraordinary detail, while simultaneously revealing its limits. The 93 billion light-year diameter of the observable universe feels immense, yet it represents only what is accessible, not what exists. Space almost certainly extends farther, possibly infinitely. If it does, then the number of galaxies is not merely large, but unbounded. Even if space is finite, its total size likely exceeds what we can observe by orders of magnitude. In either case, the observable universe is only a fragment of a larger whole. This has implications for probability and rarity. When numbers grow large enough, unlikely events become inevitable somewhere. If trillions of galaxies exist, each containing billions or trillions of stars, the emergence of complex chemistry becomes common rather than exceptional. Planets form readily once heavy elements are available. Stable environments arise around long-lived stars. Given enough time and enough locations, biological processes have countless opportunities to occur. James Webb does not detect life, but it expands the stage on which life could exist to a scale that challenges intuition. Yet, despite this vastness, communication remains constrained. Even within our observable universe, distances are so large that signals weaken beyond detection. Civilizations may exist in nearby galaxies and still remain forever unknown to one another. Beyond the cosmic horizon, communication becomes physically impossible. Expansion prevents any exchange of information, no matter how advanced the technology. The universe may be populated, yet fundamentally lonely, divided into isolated islands of causality. James Webb captures this paradox clearly. A universe that is both crowded and disconnected, rich in structure, yet fragmented by expansion, full of history, yet gradually erasing its own record. It shows us that scale is not just about size, but about reach, about what can be known and what must remain forever beyond observation. Final chapter 2 in the end, James Webb does more than reveal distant galaxies. It reframes humanity's relationship with the cosmos. It shows that we are not living in a quiet universe that slowly unfolded over eons, but in one that erupted into complexity almost immediately. Within a few 100 million years, stars burned, galaxies assembled, black holes grew, and chemical enrichment transformed primordial gas into the building blocks of planets. The universe did not hesitate. It organized itself rapidly and efficiently under the influence of gravity, expansion, and radiation. This rapid beginning shaped everything that followed. The cosmic web formed early, guiding matter into filaments and nodes. Galaxies inherited their environments. Black holes inherited their fuel. Chemical elements inherited their abundance patterns. Even the potential for life traces back to these early conditions. Without fast enrichment, rocky worlds would be rare. Without early structure, galaxies might never stabilize. The universe's present complexity is a direct consequence of its energetic youth. At the same time, Webb reminds us that this richness is fleeting in observational terms. Expansion continues. Horizons shift. Information fades. The universe that is visible today will not always be visible. Future observers may see only a small cluster of nearby galaxies surrounded by darkness, unaware of the vast structures that once filled the sky. The cosmic microwave background will redshift beyond detection. The deep past will become inaccessible. Knowledge itself depends on timing. We exist at a moment when the universe can still be studied across most of its history, when light from the first galaxies is still arriving, when the evidence of cosmic origins has not yet slipped away. James Webb extends this moment, allowing us to see deeper, earlier, and more clearly than ever before. But it also makes clear that this opportunity is temporary, defined by the same expansion that shaped the cosmos. The true scale of the universe is therefore not just measured in light years, galaxy counts, or cosmic time. It is measured in perspective, in the realization that we inhabit one small region of an immense, evolving whole, that our view is partial, time-bound, and contingent, and yet, within those limits, astonishingly rich. James Webb does not diminish humanity's place. It contextualizes it. We are not central, not unique, not privileged by location. But we are present at a moment when understanding is possible, when the universe still speaks to us through ancient light, when the story of cosmic origins can still be read. The universe is larger than we imagined, more crowded than expected, and more dynamic than predicted. It formed quickly, expanded relentlessly, and now slowly recedes beyond reach. James Webb has revealed this not as an abstraction, but as a coherent narrative written across space and time. A universe that ignites early, builds rapidly, and stretches outward forever, carrying its history with it, just long enough for us to see. When viewed as a whole, the universe revealed by James Webb is not simply larger than expected. It is fundamentally different in character from the one we once imagined. It is not a sparse expanse punctuated by occasional islands of light, but a deeply populated, highly structured system that emerged with remarkable speed. Galaxies did not wait patiently for billions of years to assemble. They appeared early, multiplied rapidly, and began shaping their surroundings almost immediately. Black holes did not linger as small remnants. They grew quickly, influencing their host galaxies while the universe was still young. Heavy elements did not trickle slowly into existence. They were forged early and dispersed widely, transforming cosmic chemistry long before the universe reached maturity. At the same time, this abundance exists within strict limits imposed by expansion. Space does not merely separate objects. It actively removes them from one another's influence. Every second, regions of the universe cross boundaries beyond which information can no longer travel. Galaxies that are visible today will one day become unreachable, not because they cease to exist, but because the fabric of space stretches faster than light can traverse it. The universe preserves its history only temporarily. Observation is a race against expansion, and James Webb is operating at a moment when much of that history remains accessible, but not indefinitely so. This duality defines the cosmos. It is generous in creation and unforgiving in connection. It produces vast numbers of stars and planets, yet isolates them across distances that cannot be crossed. It allows structure to flourish locally while enforcing separation globally. The same physical laws that enable galaxies to form also ensure that most of them will never interact. Growth and isolation are not opposites in the universe. They are consequences of the same underlying processes. James Webb reveals that the observable universe, spanning 93 billion light-years across, is not a boundary of existence, but a boundary of access. Beyond it, space almost certainly continues, filled with galaxies and structures similar to those we observe. Whether the universe is finite or infinite remains unknown, but in either case, what we can see is only a fraction of what exists. Every observer, anywhere in the cosmos, inhabits a different observable sphere, centered on their own location. No single perspective captures the whole. There is no privileged vantage point, no cosmic center, no place where everything comes into view at once. This realization reshapes humanity's place in the universe. We are not special by position, size, or centrality. Our galaxy is one among trillions. Our star is typical. Our planet orbits an average sun in an ordinary region of space. Yet significance does not come from centrality. It comes from context. We exist at a time when the universe's story can still be read, when light from the first galaxies still reaches us, when cosmic structure has not yet slipped beyond observational reach. That window will not remain open forever. James Webb extends that window. It allows us to see farther back than any instrument before it. It shows us that the universe was active early, efficient in building complexity, and rich in structure almost from the beginning. It confirms that many of our earlier assumptions were not wrong, but incomplete. The universe did not unfold slowly and cautiously. It surged into complexity, guided by gravity, shaped by expansion, and refined by feedback processes operating from the very start. What emerges from Webb's observations is not a static picture, but a dynamic narrative. A universe that ignites quickly, organizes itself rapidly, and then gradually stretches beyond reach. A universe where complexity arises early and isolation grows late. a universe whose greatest structures form while its ability to reveal them diminishes over time. James Webb captures this balance at a rare moment, when the past is still visible and the future has not yet erased it. The true scale of the universe is therefore not measured only in distance or number, but in consequence, in how early events echo across billions of years, in how small fluctuations become vast structures, in how timing determines what can be known. James Webb does not simply show us more of the universe. It shows us how fleeting our access to it truly is, and how extraordinary it is that we can see it at all. The universe is larger, more crowded, and more intricate than we once believed. It is also more transient in what it allows us to observe. James Webb stands at the threshold between what can still be known and what will eventually fade beyond reach. In doing so, it transforms our understanding of the cosmos from a static backdrop into a living, evolving system, vast beyond imagination, yet briefly visible, long enough for us to look out and understand where we are.